In this video lecture, we'll make a slight diversion to take a look at the general problem-solving thought process and how it applies to writing software. Okay, let's get started. In lots of fields of study, particularly in math, science, and various technology fields, there's a general three-step problem-solving thought process, which you've probably already used over and over again without even realizing it. In courses such as these, you've probably solved homework problems or problem sets over and over again, until this thought process becomes automatic, natural, and instinctive. In a nutshell, the three steps of this problem-solving process are these. What do I already know, or what am I given? These are my knowns. What am I trying to find out or solve for? These are my unknowns, or the desired result or solution. And for the meat of the problem, how do I transform what I know into what I'm looking for? How do I solve my problem? Or more informally, how do I get from point A to point B? This is the standard three-step problem-solving process. Let's take this general approach and make it a little less abstract by looking at a specific example. Here's a concrete example from one of my favorite subjects, physics. Even if you haven't taken physics, you've probably done something very comparable while solving math problems in the past. Here's what we're given. We have a mass of 4 kilograms to which a 10 Newton force is applied. What we want to find is the resultant acceleration of that object. How would we solve this problem? Well, we just apply Newton's second law of motion, F equals ma, and rearrange the equation algebraically to solve for acceleration. We'd substitute what we already know and calculate what we don't know. That's our game plan, and once we arrive at the answer, we'd probably want to make it obvious somehow that was indeed our final answer. So let's actually solve that problem. If we were working on a physics problem set, our paper would probably look something like this on the right-hand side. For starters, notice that we're going to define some algebraic variables for our knowns. We're going to let the mass be represented by m with a value of 4 kilograms. We'll let the force be with us and represented by a capital F with a value of 10 newtons. And we'll let our unknown, the acceleration, be represented by an a. So notice right off the bat that we're working symbolically, with algebraic variables representing each piece of data in our problem. Then to solve this problem, all we do would be to algebraically rearrange the equation F equals ma to solve for a in terms of F and m, as shown here. It's much easier to work symbolically like this for as long as possible, until we finally substitute the known values for force and mass to arrive at the numerical result, 2.5 meters per second squared. Here, all we're going to do with this result is just make it obvious this is our final answer by perhaps circling it or putting a box around it, but otherwise we are done now. So now let's extend that three-step problem-solving process to writing programs. In the kinds of simple sequential logic programs we'll be writing for starters, the same thought process applies, but with the second and third steps sort of swapped. First, we would again ask ourselves, what are our knowns, or now our computational inputs? This is where we would first assemble all the data needed to solve our problem, by declaring any needed variables or constants, initializing any data we already know, or perhaps prompting for any needed user inputs. Then, in the middle step, or the guts of our program, we would transform what we know into what we are looking for, or our unknowns, by using some algorithm, which is simply just some logical sequential progression of steps. Finally, once we've computed our outputs, we'd probably want to do something with those outputs. Maybe we want to neatly format them somehow for display. Maybe we want to return some result to some client. Or maybe we want to store the results somehow by writing them to a file or into a database or something similar. But this standard problem-solving sequence is now the flow of our code for many simple programs. In fact, one current assignment for you will be to develop a standard program template which embodies these three steps. In that template, you'll use comments as pseudocode to remind you of the standard logic flow. Let's see now what that might look like in code. Here's a visual mapping of the three steps of the general problem-solving process on the left, to the corresponding sections of a simple sequential logic program on the right. This week you'll probably be writing a first simple program template that will very much resemble this, though there will be a bit more to it than just this. The "what do I know" step is embodied by the first part of this program template. This is where we'll assemble all the variables, constants, and user inputs needed to solve the problem at hand. The middle part of this template is the guts of our program, where all the heavy lifting takes place, and where we transform the inputs into the desired outputs, using some TBD computations or algorithms. This is where the bulk of your programs will probably take place. Finally, the last part of this template is where we do something with whatever desired results we've calculated. For the time being, we'll mostly just be printing results out to the screen, but later on we'll see how to do more detailed formatting or how to return these results to some calling client program. As we mentioned earlier, notice this swapping of steps when we're mapping this problem-solving thought process into a generic program structure, but it's still all the same 3 steps. 2 other things to point out. First, notice how there are no actual executable program statements in this template. All we have right now is comments, but notice how we can use pseudocode such as this to good advantage as we're mapping out any programs we'll write. You can think of this as being similar to the brainstorming or outlining phases of writing any kind of term paper or composition. And also on the subject of comments, note how we've added a short little comment after this closing brace. This is a simple little coding practice which can help you keep track of the nesting and hierarchy of your code as it grows more complex. And I highly recommend doing this in any code you write, within reason of course. As you'll hopefully come to see, the purpose of a code template such as this one is twofold. First, if you're new to programming, this kind of pseudocode will help reinforce the general flow of a program until it becomes instinctive to you, and trust me, it will. Second, starting new programs from a template such as this one helps make us more efficient as programmers. Rather than starting from scratch and reinventing the wheel every time, we can start from something like this and simply begin adding in the details specific to each new program. Again, there will be a bit more to the template you'll be creating, but hopefully this gives you an idea of how it's structured and how it will be useful. Okay, that's enough for now on problem-solving structure in software.